Okay, welcome everyone. In this lecture, I'm going to discuss what's called Babinet's principle. And this is an important principle in the theory of diffraction or interference. And although it's often discussed, although our discussion right now is actually on single slit diffraction, I'm going to phrase this principle in a more general way, so that it's applicable to not only single slit diffraction but to diffraction or interference in general. Okay, so let's consider a slit plate that looks like this. So there are openings of these shapes, and let's consider what's called a complementary structure here. These two structures are mutually complementary. What I mean by that is this: where the slit plate is opaque, this barrier is transparent. There's nothing there. Where the slit plate is transparent, namely at these openings, this barrier is now filled with the same material here, and so this is opaque. So when you exchange opaque parts with transparent parts and vice versa, what you get is a pair of complementary structures. And Babinet's theorem, Babinet's principle is related to, is addressing the light field of these two complementary structures. So let's consider an incoming light, which let's say is green light. And on the right hand side of the slit plate, we will have some light field, which you can describe in terms of E sub S. And on the right hand side of the barrier, we will consider the light field with something called D sub B. And when you add those T's up, according to Babinet's principle, you get something. What do you get? D sub UL. And here's what I mean by D sub UL. What I mean by D sub UL is this is light unobstructed. So for D sub UL, what I'm imagining is a third situation where there's nothing. So if the light travels unobstructed, then it'll appear on the right side in some form. That's basically the original light. So that's what I call DUL. So that's Babinet's principle. It sounds simple enough, and it looks like sort of superposition, so that's pleasing. According to what we have discussed so far, this principle seems to be a valid principle, and the reason why that is because we made this very simple assumption that when the slit plate has this opening, the light gets through those openings unchanged, and so that was a very simple assumption, which is qualitatively valid for the discussion of diffraction or interference in many cases. So that's the assumption that we made. According to the assumption, this principle is, of course, it should be valid. But you may anticipate that kind of simple assumption is in general not valid. And why is it not valid? Well, because the matter and light, they interact. When they interact, the light gets modified in a non-trivial way, especially close to the boundary between material and opening. And so, depending on how that light field gets modified, you can easily maybe anticipate that this Babinet's principle will basically break down in general. Nevertheless, this simple picture that we've been using so far, namely the light gets essentially unmodified by these openings, is known to be valid in optical ranges of light. Also, so in that case, Babinet's principle is valid, and also you can prove Babinet's principle in case when the slip plate is made of very thin material, infinitely thin material, and infinitely conducting material. You can actually prove theoretically this Babinet's principle, and so so that's the theoretical content of this Babinet's principle, and so it can be used in many situations in a useful way. And so let's discuss what this Babinet's principle implies in terms of diffraction pattern. Well, before I do that, let me actually, since I was discussing some theoretical aspects of this principle, let me mention that what we call D here is the light field, and the light field is described in terms of electric field and magnetic field. And so it turns out this Babinet's principle in the case of light, you have to actually mix electric field and magnetic field in general. So what I mean by that is that this D may be electric field, but that D may be magnetic field. So this Babinet's principle is valid in the case of light field, but in a slightly more complicated way than is implied by this simple equation. So in any case, let's look at the consequence of this Babinet's principle on diffraction or interference pattern. So the example that I will do here, I will make it very simple just to demonstrate the consequence, but I'm going to generalize this right after. So first of all, let's use some green light here in the form of laser beam, and I'll make an assumption that this laser beam is a cylindrical beam, which is a good approximation for a laser beam over a short distance. And let's see. Let's consider a slit plate which is very simple. So I'm going to consider a single slit, a circular aperture. Okay, a single circular aperture, and so I need to I don't want to use capital D here, so let me use this as H. H is the beam size of the laser. Let me use small h for the size of the aperture of the slit plate, and I'm going to assume that H is much less than capital H, and that's a good assumption, because what you want in this type of experiment is to flood this aperture with light. So what typically happens is that you use a laser beam which is much greater in size than the single slit or any other structure that you're shining on. Okay, so then what happens? Well, then this diffraction pattern will be this called what's called Airy disk or Airy pattern. So what you have is hold on a second. It's a central peak, and then fringes, and then a third fringe and things like that. So these dark fringes will appear, and then the central part is very bright, and this second ring is less bright. I mean, it's only a few percent bright, and then it's even less bright in the third bright ring, and so on and so forth. Okay, so that's what happens. Now we ask the question, can we actually determine the size of this thing, this diffraction pattern, the central peak? Yes, we can. That's what we've been doing in previous lectures. This is what we called y, and that's L tangent theta. And let's assume that theta is very small, and in that case, this is L theta, approximately L theta. And remember, the diffraction condition for circular aperture is d sine theta equals 1.22 lambda. So because of that, and because sine theta is about theta, we can say d theta equals 1.22 lambda. So then this theta becomes, so d in this case is h, small h, 1.22. And I'm going to throw away that 1.22 for qualitative discussion here. What we're really after is the order of magnitude. And so it's approximately on the order of L lambda over h. So now let's consider the complementary structure here. Instead of this, let's consider a disk. Disk of the same size. Then what would be the what would be the output light for that disk, diffraction from a disk? So now we look at this principle and seek our answer. Okay. So what you need to consider is then what is the the unobstructed light. So here we make another assumption that there's a subtle point here. Well, maybe your gut feeling is that this unobstructed beam will just appear as the beam of size h. The laser light should just go with the same shape forever. But that's actually not quite true, right? You know that, because this laser light, if it's unobstructed, over a short distance, it will definitely go, unmodified in shape. But as it goes through, it will actually diffract also. Why? Well, because the way that I drew it here is just a pencil-sharp cylindrical shape of beam. And what is the difference between that initial condition and maybe some plane wave that's blocked by a circular aperture and made into a cylindrical beam by the slit? Well, the initial condition is the same. For a diffraction through an aperture, to a circular aperture to occur, all we need is to get a plane wave and make a cylindrical beam. Here, we assume that the laser has a cylindrical beam shape, and if that's the case, it should diffract too, right? And so we will assume that the distance from the slit plate or the barrier in the form of a circular disc to the screen is so far away so that the same diffraction formula applies to the laser beam as well as to the slit plate and circular disc. This assumption amounts to saying that Fraunhofer diffraction, the so-called Fraunhofer diffraction condition, is applicable to all these structures here: the beam, the aperture, the circular disc, and so on and so forth. And in fact, although we were not explicit about it, this Fraunhofer diffraction condition, diffraction assumption, is what we've been assuming all along. And you can look at my written lecture note on double slit lecture to get some more information on that assumption. In any case, okay, so this circular beam of laser also diffracts. So then what happens on this screen? What happens on this screen? You can figure it out. I'm not going to draw anything here, but the y for that laser beam is given by L lambda over large H, right? So that means the diffraction pattern from the laser beam itself, so the diffraction from this DUL corresponds to bigger size or smaller size on the screen. It's smaller size, right? Because the beam is much bigger than the hole here. What you will get is actually you will get smaller, much smaller central peak here, and then a few fringes appearing on the side. But the intensity of those fringes will decrease very rapidly, and so by the time you get to the first dark fringe, due to this circular aperture, when you come to that angle, the diffraction pattern from this laser is all gone. The intensity is all gone. So that's it. That's the main point here. So the main point here is that where these dark fringes occur, right? DUL is basically 0. The reason is because of this. Large H is greater than small h. Because of that, at angular positions, at the first dark fringe and the second dark and greater angle than that, the unobstructed light basically has 0 intensity. You know what that means? Think about what that means. This ds and dB dB is given by negative ds except near center, near center of this of the screen. Other than near center area, DUL is close to is basically 0. So that means the light from the circular disk, light from this circular aperture, they basically have the same pattern, same amplitude, except that the amplitude is reversed. That's it. Guess what that means, right? What that means is this diffraction pattern is precisely the same, except for the intensity at the center between this circular aperture and the circular disk. That's the practical implication of Babinet's principle. And some of you may verify this if you have a laser pointer by pointing laser to a hair. And if you do that, you will get a diffraction pattern which is basically the same as the diffraction pattern from a single slit of the same width. Of course, this discussion can be generalized to a more general case where the slit pattern is not just a single slit, but you can have any kind of a funny pattern like this. But in these general cases, what you need to consider is that this slit patterns have some length scale, right? So this length scale, you will define that as small h. So the top of this pattern to the bottom of this pattern. And so you will define that slip pattern as h. And you can apply basically the same qualitative argument. So in those cases, in a general case, this h, small h, will not be the diameter of a circle, but it's basically the maximum size of patterns that you make in the slit. And then you can consider a complementary structure, and then what you will get is that in either case, the diffraction pattern or the interference pattern will show modulation, whose angular position is given by the same formula here. It's basically L lambda over H. You can look back all the formulas that we studied before, where you consider double slit. In the case of double slit, this small h will correspond to small d. In the case of n slits, this small h will correspond to the the end-to-end distance of the slit. So that's what we called. I think that's what we call capital D in that case. So anyway, in all those cases, the angular modulations of the intensity pattern appear basically the same, following the same pattern here. L theta is approximately equal to L lambda over H, where H is the maximum size of the patterns that you make. And so therefore, exactly the same argument applies, except that this airy pattern should be replaced by the particular pattern that's appropriate for the slit pattern that you make. So that's the basic content of Babinet's principle and implications from Babinet's principle on patterns that you observe on your screen.